Hello. So I'll be going over my next episode of my machine learning notes. I like to I'm going to be covering neural networks, LSTMs, RNNs, and word embeddings. So neural networks could be seen as a collection of nodes and their connections between the nodes. An example so each of these nodes could be represented with the value between 0 and 1, or it could be some random positive or negative integer. An example could be, it could be like true or false, like do they have like a feather for a bird, true or false for image recognition. Or it could be like an arbitrary value multiplied onto a stock price by a weight, and it goes to the next node. So weights are parameters that you multiply, biases are parameters that you add. There's many different activation functions: softmax, sigmoid, and ReLU. So each of these nodes could have a different, soft plugs, but each of these different neurons or nodes could be seen as having a different activation function, which you could assign in the TensorFlow on the sequences library. So, in a neural network, there's only two parts you really kind of know exactly how to make: the input layer and the output layer. So, the output layer. For the output layer, you could have multiple nodes if it's for example, a softmax, like a image classification, like telling what type of bird it is. But you might only use one node in the output if it's like a true or false, like is it bird, yes or no. You only need one neuron at the end with a sigmoid function, for example, to make it between 0 and 1, and you could tell if it's a bird or not. For the input layer, it's a little different. Like for images, you could have like all the RGB values and the list of all the pixels, and then make it a tensor, also known as a more efficient version of a matrix that you plug in and use as the input layer. And this could be represented as a bunch of different values, or an array, or matrix. And it goes through different weights and biases that multiply and add them, which are then, through back propagation and gradient descent, modified so that we get the correct output from the corresponding input. And the input layer could also be not just the colors, it could also be the word embeddings, which are a way of saying the word's meaning, or which is a token. It could be like a token's meaning, which are usually trained through neural networks and could be used to show in a space what the word means. So, this will be covering backprop first, which is the use of the chain rule to find the partial derivatives to update the weights and biases in our neural network. So the steps are: first, find the partial derivatives. Step 2, plug in the derivative values into gradient descent to update the parameters. The step size that is used in gradient descent is slope times learning rate, and the slope is the partial derivative, and the learning rate is predetermined. And the learning rate could be changed in certain optimizers, such as atoms. So, I'll be covering argmax and softmax, two different ways to show a classification which could be used in images to determine what is this image. Like, is it a different type of species? Like you have multiple different possible outputs other than a yes or no. Argmax looks at the output layer and looks at all the values, and then sets the largest value to 1. All the other ones kind of get ignored. Since the output only has 1 as a value, and the value and only the other nodes, their values before being converted to argmax can't really be seen. It's kind of like rounding. Since it's after it got rounded, it can't really be used to optimize. Like, how do you know the steps of their work if all you see is the answer? With softmax, instead, each node outputs a value between 0 and 1. All the nodes add up to 1 in softmax. So in this case, it could be optimized because you can see how much the model predicted each result. So it could see like, oh, it didn't predict it was a hummingbird. It actually predicted it was an emu. And emu was like the very last. So maybe that allows the to change the parameters more and tweak it until we have emu a little higher up. And the loss function for both argmax and softmax is cross entropy. And the main difference, for reminder, is argmax can't use backprop, softmax can. And you can see how I calculate the softmax value. All I do is take the previous output layer, and before doing softmax, e to the value over the sum of all the e to the x values from the previous output layer to convert it to a softmax output layer. So, RNNs could be seen as a way to help predict values. Like, for an example, you have all the days of a week as data. You don't want to just use the 6th day before the 7th day, which you want to predict, as the only value you use in your prediction. So, how do you predict the 7th day? Well, you could use something called recurrent neural networks to use to train the weights and bias to go from the 1st day and drag it out to the 7th day and predict the 7th day using the day 2, 3, 4, 5, 6 to train the RNN at each time it reaches that day. So how does an RNN reach the next day? So you first start with the initial input, which is the original first box. Then you multiply it by the weight, add the bias, and then you put it through the activation function. Then you put that result and put it back into the previous weight and multiply it and add it with the bias. This is called rolling, in my opinion. And you roll it until you reach the day count which you want to find the prediction for. So let's say I only want to find for day 2. I don't really do the rolling. I just give the result of my activation function. But let's say I'm going from day 1 to day 7. I have to train from all the days I have, which are day 1 through 6. So I look at day 2, look at the prediction, see if it matches the activation function. If it doesn't, we do backprop, start adjusting. Then we go to use the result from day 1 to get day 2, which we use to get day 3 by going into the rolling. And there's some problems with RNNs. It makes training a little hard because of all the rolling you have, and it has exploding vanishing gradient problem. So what's an exploding gradient? Well, let's say the weight, W1 for this example, was 2. And let's say you multiplied it to the power 20 because you rolled it 20 times. Well, 2 to the power 20 is a very large number. And after a certain point, it's so big you can't really tell anything from the results. The opposite could happen, where the weight is a small value, like 1/2, And then after 20 times, you're practically at 0, so you get no information from it. So, how do we solve the exploding and vanishing gradient? Or how do we not lose our information after the weights are multiplied so many times that we just lose all information and we just get a huge number or 0? This has a solution where we go over LSTMs, long short-term memory. LSTMs, long short-term memory, they use two different functions. They use the sigmoid and the tanh function. The sigmoid function squeezes a value between 0 and 1. It's e to the x over the e to the x plus 1. Tanh makes the value between -1 and 1, e to the x minus e to the negative x, over e to the x plus e to the negative x. So the steps for an LSTM. 1. Forget gate. Forget past long-term memory. Has no effect if the initial long-term memory doesn't exist. 2. Update long-term memory with the new input. 3. Output gate. Update short-term memory with long-term memory. 4. Repeat until it goes through all the inputs. So you might be asking, how does it work through all the inputs? For an example, it could be a sentence, and you have each word, which is further turned into an embedding vector, which could be show the value of the single word. And then you go through each word, and then you put it through the LSTM, where it updates the long and short-term memory, and then you output the short-term and long-term memory at the very end of the sentence. So word embeddings are a way to convert words to vectors. This is commonly done through neural networks, and you normally need a lot of words to train a word embedding model. So let's say you have a list of possible words and 1 or 0 to show that the word is there. Then it goes through different nodes. Then it goes to the output, which is going to be, in this case, a softmax, predict the next word. Then you continuously backprop till it predicts the correct next word. Like after bird, it might predict is. So you keep on backpropping till it predicts is, and then you take the layer in between the input and output, and those numbers associate to the word, which in this case could mean embed. It's an embedding.